Welcome back to 1-Bit Fever Dreams. One of the things that was often hard in programming back in the old days was anything dealing with sound. Usually you start with a typical basic instruction that emits a beep at a certain frequency. In Microsoft Basic 2.0, all you need to do is this little short line. If you actually want to play a little tune, then you need to learn about other values to send out, and before long, you're consulting the annex of your documentation in order to reach all the notes of all scales. Congrats, you just unlocked modal tunes, meaning the instructions playing your piece of music will act alone while everything else stops. And you know what? That sort of crude way of doing things was widespread in the early days of Mac gaming. You would very rarely see music during gameplay that also involved moving graphics or arcade-like controls. Because the sound of the Mac notoriously involves a lot of CPU cycles in order to operate. Many developers simply accepted this as a fact of life and just put music in the title or transition screens. If you wanted real-time sound during gameplay, then it's much harder because you'll have to dive in the complex and rich world of interrupts, callback functions, and cycle counting to make sure it stays smooth. However, one extremely popular game of the 80s did this. This is running, of course, on my Macintosh Plus from 1986, but this great sound is not coming from inside this box. It's outsourcing all the audio manufacturing to this, a Roland MT32 module that uses MIDI signals. Achieving the same result inside this Mac Plus would prove to be too hard for this poor 8 MHz CPU, especially when you start involving all 16 channels and add on reverb effects and instrument patches. All you need to do to make the connection was to get a MIDI serial interface box. Just run a serial mini DIN cable from the Mac to this box, then a regular DIN 5 cable from MIDI out here to MIDI in here. And you're good to go. There's no system extension or driver to install. The Sierra people did their homework in Space Quest 3 to make the two machines talk to each other with an internal in-game driver that you activated with the game's setup utility. I don't know who had the money to get this gear back in 1988 to pay for a $700 MT32, which is shy of $2,000 in 2025 after inflation, but I distinctly remember seeing a demo set up in a computer store called Crazy Irving Le Fou in Montreal in the late 80s. I was blown away because it was immediately leagues beyond any other music sound I ever heard in Mac games or any other platform altogether. But let's get back to the main topic. I'm doing this video because last year, the idea of reverse engineering what SQ3 did with MIDI using C programming got stuck in my head. Let me explain my train of thought. 1. Programming music and sound the normal way on the Mac requires some solid reading, and while that's also interesting, that's not what this video is about. I promise you I am going to explore the Macintosh sound driver in another video, because I think it's rad. It has its own charm and quirks and doesn't depend on owning any additional hardware, unlike MIDI. 2. The MIDI specification dates back to 1983 or so, and it exists on its own. It has a rich history and still exists to this day. It's a fun programming goal on its own and transcends all platforms. Even if you don't particularly care for the Macintosh side of retro development, you can still learn a thing or two here and port it to your favorite machine, even in microcontrollers if that's your thing. Three, MIDI is just a stream of serial bytes and has good documentation, so it's easy to dissect and program. You can limit yourself to just the commands that are tied to the actual sounds and ignore the rest. It'll reduce the difficulty of programming for it by a lot. 4, it sounds like $1 million. Compared to the crude square wave that was used in the earliest Mac games, it absolutely feels like cheating and I love it. Outside of sequencer programs like Cubase, Mastertracks Pro, and other musician-type pieces of software, and of course Sierra for the gaming side, I'm not familiar with any other usage of MIDI that was done in the 80s for Mac games. So in a way, this is treading on a very lightly used path of the compact Macintosh years. The goal is to create a little C library for it that you can use for your own projects if you decide to go all the way with me in this rabbit hole. If you're already well versed in MIDI and just want to see how I implemented it for the early Macs, you can skip this section. For the rest of you, here's a brief MIDI crash course. It doesn't need a computer at all. It exists as a language between digital music instruments. However, of course, computers have latched onto this MIDI party since they can run software that controls the hundreds of settings it can allow, derive softwares that deal with it such as sequencers, DAW, loopers, and so on. But MIDI as an exploration topic for retro programming is awesome. MIDI crosses all platforms of all decades because it exists on its own merits instead of just being an add-on for a specific computer ecosystem. This is the simplest use case. A synth piano-shaped controller that has keys, a MIDI controller, and a sound wave producing chip all in one. Plug in some headphones and you're good to go as a musician, no computers involved. The next step would involve a MIDI cable between a controller and a MIDI module because you're outsourcing the sound wave producing task to the second box. A lot of pro musicians started doing this in the late 80s and 90s to dramatically improve their sound. Then we have computers joining in the party in the 80s. One notable example is the Atari ST and variants that add a MIDI out port right there in the back. The computer takes on the role of the controller, but they still needed an external device for the sound wave. The 8 MHz Atari had the same problem as the Macintosh. The CPU wasn't enough to mix sound waves of enough instruments at the appropriate depth in real time. Connections are established with MIDI out and MIDI in sockets. The in or out are telling you in which direction the data is flowing at this precise location. So you typically want a MIDI in cable connected in a module and typically want a MIDI out connected on a controller, whether it's a piano-shaped object or a whole Macintosh trying to play a piece of music. The information flows in a serial fashion where every byte is sent in a 10-bit package, 1 start bit, 8 data bits, and 1 stop bit. This means each byte takes up 320 microseconds to flow. Most MIDI commands need a variable amount of several bytes to express a well-formed command. At this point, I'm only going to show you a few of the most important ones and how they look. From a programmer's perspective, this is where you'd insert your if-else-if conditional blocks or your switch case block in order to react to them properly. The most important command is called note on and would look like this. The highest half of this byte, aka the I nibble hexadecimal 9, means we're about to start sounding a note. The lowest nibble, being hexadecimal 0, means we're targeting channel 0 on the MIDI connection. There are 16 channels from 0, 1, 2 all the way to C, D, E, F. If we changed it to this, we'd send a note on command to channel 5. Let's keep it that way for the time being. In order to complete this command, you need 2 more bytes of information. The note you want to play and the velocity, meaning the force you used to strike a note on a piano controller. The middle byte, hexadecimal 3C, denotes a middle C on a piano, fittingly enough, the 3rd octave C. The last byte is the maximum value for the velocity, so it'll sound nice and striking. Congrats! You can now produce MIDI sounds, and the most important part is covered by just this command. The hard part is knowing where to send these bytes according to your specific computer needs. However, some instruments will hang on for a long time and you must turn them off, otherwise you could have a cacophony. This is where a note of command is used. Just replace the value of the high nibble from 9 to 8 like so. In order to work, you must select the same channel you used for note on and the same value of the note that you used for that note on. The velocity doesn't need to be the same at all here. I don't want to make this crash course too long, so let me just add another very useful one: how to change instruments. In the general MIDI spec, this is the standardized list of instruments you get in each MIDI module. While they may sound different because of the samples and timbres they used, they at least try to recreate the spirit and intention of those instruments, so that you get a semblance of uniformity. It's the change program command, and it's even shorter since it only uses 2 bytes. The C means change program. The 5 still means target channel 5 here in this example, but remember you can point it at any channel you want from 0 to F. Hexadecimal 22 translates to 35 in decimal, which is the fretless bass. These commands change the instrument of your channel whenever the command is transmitted, and you don't have to stay put with just one instrument per channel. You can change it fairly quickly between each note if you wanted. Remember that every byte takes 320 microseconds, so a change program command is just a mere 640 microseconds. Nothing would stop you from exploiting this and making all of your 16 channels use more than 16 different instruments in total. Now that this very brief crash course is over, let's see how to get started on the old Macintoshes. Right, but what do you need for MIDI in the early compact Macs? Since the MIDI spec calls for a serial connection of exactly 31,250 BPS, but the Mac serial port doesn't support this natively among all of the choices that you have. So you need an external interface box with its own crystal, typically 1 MHz. It's all done for you with a divide by 32 in the circuit to get down to the right speed. If I am to believe this Cubase settings window, there must also have been interfaces out there with half the speed at 500 kHz. Apple released its own official interface back in the 80s, but there were many third-party releases as well, such as this Anatech. It works with the passive power of your Mac's serial cable, and you typically need to choose a port between the printer and modem one. There's no real advantage in picking either one. The MIDI out port is where you plug your cable that goes out to a MIDI module. Let me repeat that the sound protection is not made inside the Macintosh itself. It needs to outsource this crucial step to something else. If you want to enter this rabbit hole eventually yourself, there's a good number of modules in the used market out there at okay prices. You may also opt to reach for an emulated device based on the Raspberry Pi 3 and above, or the Pi 0 and above, which is called the MT32 Pi. This project can be either bought assembled or done as a DIY kit. Contrary to what its name suggests, it does more than just emulate a Roland MT32. It can also do a number of later general MIDI modules through sound fonts. For more information, check the links in my description. And now we get to the programming side of things. This was the trickiest part by far for me because the documentation from these olden days are found in ever-shrinking specific spots on the internet. It only still exists because of people passionate by retro computers. Many thanks to these countless people. I sincerely couldn't have done this project without the help of these helpful folks in the 68KMLA forums in no particular order: MK.558, Michael Engel, YMK, RB, and mostly Joe VT, who fired off multiple suggestions as I tried to parse documentation that was initially meant for later Macintoshes first, as well as assembly source code that I had to adapt and whatnot. My IDE of choice is still semantic, think C++ 6.0, but I'm only really using Macintosh Standard C. Let's check the lists of steps that you gotta add to your C program. You have to open one of the serial ports. The star of this routine is the toolbox function open driver. I start by opening .a_out, which is the modem port here in the outbound direction. It's weird that you have to name that port name with a Pascal style string, but hey, I promise you it's not the weirdest thing you'll be seeing until the end of this video. You can also open a .ain if you're interested by receiving MIDI bytes from the external world. Keep this in mind because that's how we'll be able to play a piano and make the Mac react to it. You can adapt your error checking and error messages, of course. Pair it up with a close serial port routine shown here. It closes both A_out and A_in ports, or your application will make your system unstable as you exit the program. If you needed to instead use the printer board, then replace letter A with letter B. Next up is the handshake options routine. I had no idea how to do this initially, and it's only by reading old Mac Tech articles and Apple documentation that I figured it out, getting validation from forum members. You declare a shake, serial handshake, record with these settings, and then tie it up with a control call, which is a device manager function that sends control information from memory to an open device driver. The CS code that you can see here in the middle as the number 14, well, that sort of stuff was found digging in the Apple technical notes. I couldn't see a list of devices in my usual source of information, the Think reference viewer. You gotta tweak the clock of this whole serial operation, or otherwise everything will be out of sync fast, even if you pick the closest possible speed from the ones you used to have with modems, such as 33.3 kbps. MIDI needs exactly 31,250 bps and doesn't have a lot of margin of error. Again, I don't think I would have figured out this step without the gentle guiding hand of Mac forums. A hard-coded address of X1DC is used, and we're sending custom values at the third byte by using ADDR2. We're sending two commands here with some dummy delays to avoid being too fast and overwhelming this serial device. Here's the whole thing step by step. Point to write register number 4, which is the transmit receive miscellaneous parameters and modes, followed by a dummy assembly copy command of this SP register onto itself. Just to wait 2.2 microseconds as a delay, we're gonna insert a delay between everything from now on. Now that WR4 is selected, send it to hexadecimal 84. The 8 nibble sets it at times 32 clock mode, and the 4 nibble sets it for 1 stop bit and character. You can see the effect of every cleared bit by consulting this chart. After another delay, we turn our attention to write register 11, the clock mode control. We send it to hexadecimal 28. The two things that are set are D5, which means we're getting a receive clock as getting its value from the transmit pin. Then D3 being set means that the transmit clock will also get its value from the same place. This makes the MIDI interface basically dictate at what speed everything will happen, which is a good thing since this class of Mac I'm using can't do it internally. If you're wondering what source of information contains all of this wizardry, it's in the Zilog Serial Communication Controller User Manual, since it's the chip that is used in compact Macs for anything serial. Normally, Mac users just use extremely dumbed down programs to set the ports to their needs, like Chooser, where you get to select if you're using a printer or a modem on your serial ports, or where you plugged in your serial MIDI interface in Cubase, but we needed to get down behind the curtains in this programmatically driven MIDI goal. Annoyingly, we have to set up yet another thing, a parameter block record, in order to send stuff to the serial blocks all in one go. That's the last barrier between our will to do music and actually hearing it, though. This union type structure is defined as such and controls how many bytes are sent at once. Our needs will mostly be covered with 2-byte commands and 3-bytes commands for the most part. If you want to start with MIDI on and off commands, let's set it to 3 for now. I'm using a global param block that I'll use over and over again, and the only thing that will change is the actual 3-byte message so I can move up and down across the notes. Very important line here where you set up the I/O reference number to that output port ref number we opened earlier in the first step. And finally, the PB_write function sends your actual param block record to the serial port. And we're done! When I worked on it last year, I built around a text-driven console-like application where I could input text commands to make it do some MIDI tests. This form of app is really good to easily give you automatically scrolling text feedback and is great for troubleshooting. Also great at accepting commands without forcing you to program a menu interface, clickable buttons behavior, and such. Eventually, having a Mac-like interface driven by a mouse is the end goal. But while you're doing a proof of concept, it's great to do it this way in a much more classical type of C programming. I covered how to set up ThinkC to let you do this in my intro video I made years ago. The key thing is just to include the NC library in your project window, include standardIO.h, and just happily use your printf and scanf. I'll be running my app here, and I made a little custom icon for it in ResEdit. I'm getting positive feedback as it sets all the steps I spoke about earlier. Let me power my Roland sound canvas and Roland speakers so we can hear sound. One of the first tests I did was to play a pre-built C scale on channel 1 default grand piano instrument. It took many attempts to get to this step, many posts of back and forth, but this was my reaction when it finally worked after a few days or maybe even weeks. Before it was working, I set up a breadboard circuit to intercept the MIDI signals and check them under my oscilloscope. I always say every time you find a need for a scope is a good day. I used a very well-known MIDI-in circuit that you can easily find online in the MIDI-in or vintage PC side of things, since it's how you basically build cables or adapters whenever you want to bring a MIDI signal to any module, box, or computer. It unfortunately needs an opto isolator that many might not have readily, but the good news is that they're cheap. I'm using a cheap H11L1 chip from AliExpress. The rest is resistors and probably a MIDI-in socket if you want to make an easy connection. I'm using a dummy load resistor of 1k ohm. You need a scope that can sniff out bytes, and it has to be set up with the same start and stop bit configuration that is in the MIDI spec. Here's the detection of a middle C. Here's a G sharp. I was feeling really good at this point. The hardest work was done. But to make this useful and enjoyable, the next logical goal is to leverage standard MIDI files and send it out to the same output port. So I want to build a MIDI file player. All it really boils down to is that they are a list of these 1, 2, 3 or more bytes of MIDI commands. They have a header that gives critical information used for the speed of the playback and less important description text strings. Every MIDI command is preceded by a timing information called MIDI ticks, which require a bit of calculation in order to be translated into meaningful time when used in a computer. That'll have to wait for the part 2 video. There's a lot to cover, so it makes sense to stop here. Even with just part 1, someone could take in my code and run with it. You could program a piece of music software yourself without relying on a standard MIDI file format. All you'd need to do was to send MIDI on and off notes in order, set a time manager routine to force the delays, change the instruments, and even send text messages if you were using the Roland MT32. I'll be putting all of the code of this video in my GitHub repo called 1-Bit Dream Machine. It's my long-term goal to fill it up with C library files that manage graphics, sound, including MIDI, time stuff, and miscellaneous useful functions that will help someone program a game for the Macintosh Plus mainly. It'll probably be useful for similar machines such as the SE, the SE30, or later 68K. As always, take care, and I'll see you in the next one. I'll leave this preview of a MIDI file player I'll show next time. It's playing a tune from Warcraft 1 from Blizzard.